This is Greg Troutwine with Marine Technology TV, and we're here today with Grace Saba, the Assistant Professor of the Center for Ocean Observing Leadership, Department of Marine and Coastal Sciences at Rutgers University. Grace, to start us off, can you just give us a short introduction of yourself and an overview of your responsibilities?
Sure. As you said, I'm an assistant professor at Rutgers University. I teach, I do research, I do serve in a bunch of different service roles at the university, but also nationally and internationally. But my research focuses on the ecology and physiology of marine organisms, specifically how they respond to climate change and environmental stressors like warming seawater and coastal ocean acidification. So in that research, I do lab and field-based experiments and observations, but I'm also one of the faculty in the Center for Ocean Observing Leadership, so RU Cool group, where we run one of the most advanced observatories in the world. And we specialize in underwater gliders. So the Slocum web glider specifically is the glider tool that we use. And so I now am using gliders to observe habitats. And I observe habitats because it's important to understand what these marine organisms are exposed to. So that's why now I'm incorporating these observations into my research to better understand how they will respond physiologically.
But can you give us an overview of your ocean acidification project, specifically when and why it was started and what stage are we at today?
Sure. It's kind of a weird story. It didn't start purposefully, really. I was really looking into designing experiments to expose marine organisms in the mid-Atlantic to ocean acidification conditions to see how they responded. And the problem was I couldn't find, I realized we didn't have much data to design an experiment and to really understand what the natural conditions were, and specifically what the natural variability of those conditions were. So it almost became impossible to design a realistic experiment. And so that's when I started looking into some observation tools to get some more data so that we could design some better experiments. And being part of the COOL team at Rutgers that uses the gliders, I naively asked, why can't we just put a pH sensor onto a glider? And at the time, it was because the pH sensor hadn't been really developed. That was about 10 or so years ago. It wasn't developed to be able to withstand changes in pressure, so going from surface to the bottom, which is what the gliders do when they're profiling. But luckily, we have some really good people that had worked to develop that sensor. And so that was a collaborative research with Seabird Scientific, some folks at Mbari, and then Scripps Institute of Oceanography, and then also I think Honeywell. So it was a big collaborative group that was working to develop. They were able to withstand the pressure changes on the pH sensor. And then they started testing those on the Argo profiling floats. And so once they got to that stage, and they were successfully tested on those floats, I knew it was time that we could possibly try to do this on a glider. And so I reached out to Seabird Scientific and Teledyne Web Research to see if they were interested in seeing if we could do that. And they were very eager to get involved and just give it a try. So we collaborated together on a proposal to the National Science Foundation Ocean Technology and Interdisciplinary Coordination Program. And it was successfully funded. And so then Seabird Scientific and Teledyne Web worked together to actually make some modifications to the sensor that they were using on the Apex profiling floats. And then we integrated it into a glider. And then through our Rutgers glider program, we did some deployments with it, and we were overjoyed by how well the sensor seemed to work and how robust it was. It provided highly accurate measurements of pH in the field for weeks at a time. And so we were extremely happy with the first set of testing. And so now we're at the point where we're kind of applying the technology to see if we can cover larger spatial scales. So I have a project with NOAA Ocean Acidification program to see if we can, fit several gliders now with these sensors to get a better picture of ocean acidification on a much wider spatial scale, to look at seasonal dynamics and start looking at what really causes or what really drives acidification conditions in these regions. So that's where we're at now. We're still kind of we've developed a sensor and now we're kind of in the application phase.
How important is it, these relationships with these technologies and technology partners to work with you to help deliver the tools that make your job easier?
I don't know if it can be done any other way. I mean, I don't have a lot of experience working with technology. This was actually my first glider project. But I just couldn't see any other way to try to do it, especially when the sensor wasn't developed. I think the partnerships are extremely valuable because, you can work with industry, they can help design the sensor to fit the needs of the research community. And then, we can work with the research community then to test the sensors and to make modifications and improvements to the sensors to meet those needs. And these, for ocean acidification, there's so many different stakeholders that are interested in the data. So there's obviously the researchers, so that would be me, people like me. But there's, fisheries scientists, there's water quality managers for states, on the state and national level, policymakers. So that it really does contribute to the needs of a lot of a diverse range of stakeholders.
So Clara, obviously, Grace had some very nice things to say about the Slocum glider and the cooperation with Teledyne in this regard. Can you just give us an overview of the technology for this project from your perspective?
The glider, it's kind of a great story, was originally developed by Doug Webb to be a thermal glider and to get its energy from the thermal characteristics of the ocean. And he showed it to Rutgers University, and they immediately said, wait, that's so great, we need batteries in it because we need it tomorrow. So we put batteries in it, and now we only deliver gliders with batteries now, and we've delivered over 800 now. So throughout that, Rutgers has been a strong collaborator, and we have integrated multiple sensors with them and applications. We've done long-term piloting with them. We've been working on a mission to fly gliders around the world with Rutgers University. So the unique qualities of the glider, the quiet flight, the long endurance, and the low cost have been a good match.
Again, if you can discuss the project and some of the results that you've now seen to date.
Yeah, so we've done several deployments, and what we're really looking at on the shelf in the Mid-Atlantic region is seasonal dynamics. So we want to see, because with the existing data we have, we're very limited on the seasonal data dynamics on the seasonal scale. So we have, and the other issue and the data gap that we have is data for subsurface measurements. So we have a lot of surface measurements, which is great. And it can tell you, if those measurements are being taken over long periods of time, you can see change over time. But the bottom is really important because we have a lot of calcifying organisms. Our big commercial shell fisheries live in the bottom waters. We have a lot of fish species that live in the bottom waters. And the bottom waters are typically susceptible to low pH or acidic conditions because, especially in the summertime in the Mid-Atlantic, we see such a strong stratification in the water, which means the surface is really cut off from the bottom and there's not a lot of ventilation. So, it can become low in dissolved oxygen and low in pH or more acidic. And so what we've seen with the gliders now is we've seen dynamics over time. So during a year, we can see those seasonal dynamics. So what we really see is in the summertime, when we see that high stratification in the bottom water is where we typically see the lowest pH during the year. And it's important to know the timing because you can time it with organisms' life history or their phenology. When are they reproducing? When are these shellfish spawning? And so you can kind of start timing or better understanding time periods where organisms might be more sensitive. So we're seeing that in the summertime, but we're also seeing differences in space. So near shore, we get a lot of fresh water coming in from our rivers and our estuaries. And that actually acts to reduce pH or cause the water to become more acidic near shore. And then offshore, we have something completely opposite where we have this warm, salty water just sitting off the shelf, and that's influenced from the Gulf Stream. And during mixing events like storms, but also during fall when we have these heavy wind periods and the water starts to kind of turn over and breaks up that stratification, we actually see relief of the low pH from the summer on the shelf. And so that mixing acts to really just kind of mitigate ocean acidification on the shelf. And so the organisms can then maybe breathe a sigh of relief in the fall when that happens. So those are the kinds of things that we're able to look at now. And now we've expanded it in space through this new project. So we will have gliders flying in the Gulf of Maine, and then in the North Mid-Atlantic Bight and the South Mid-Atlantic Bight. And that's really going to just allow us to better understand properties in different water masses and kind of see what the source waters are doing and how they're feeding in to different parts of the region, and then how that affects ocean acidification.
When you look at this project today, can you share with us any lessons learned?
Well, for me personally, it was the first project I've worked with gliders, and come as a biologist, it was a lot of fun, first of all, but also the partnerships made and the opportunities provided to students has been amazing. They've been able to work with this technology. They've learned a lot about chemistry just through working with the sensor. So it's providing a lot of STEM education to our graduate and our undergraduate students, which is awesome. And then, we have challenges with the sensor. So we're working with Seabird to help mitigate some effects of biofouling, which we do see in our summer deployments because it's warm and there's a lot of biology happening in the summer. So, we're learning lessons on now how to improve the sensor design for future applications. But so yeah, it's really just been learning how to use the gliders for me personally, but also being able to apply that and fill some huge data gaps that we see regionally and nationally and globally.